My pleasure to introduce this afternoon's speaker, who I have known for just a little bit of time, but I've been very impressed with. Sangbei did his undergraduate degree in Yonsei, if I said that correctly. And you may or may not know it, but he actually was part of a startup company for a while. But you don't know what happened to the startup company.
It's doing okay.
Okay. Then he went on and did a PhD with Mark Kowski at Stanford, in which he developed a whole slew of really cool designs that are stuff that, well, I'm sure you'll hear about it, but things that manage to take advantage of insights gained from biology without actually copying biology. And I think we're going to hear a bit more about that. So,
Thank you so much. Thanks, and also thank you for coming to this precious afternoon, Friday. I hope that I can entertain you enough. So I have always too many slides, so I'm going to move on. So I just want to let you know the title is about new design paradigm for mobile robot. So mobile robot can be many things. I'm talking about terrestrial robot, walking like us on the ground. So robots are really hopping nowadays. Toyota just announced a $1 billion investment is managed by Gil Pratt. Actually, Gil Pratt was the manager of our robot in the DARPA program. And there's a Korean company, Korean Yao, is coming next week as well, and they're investing not as much as Toyota, but like 100 million and so on. But really, if you think about robot in your life, this is actually the robot that have a strong impact in our life. And then this is state of art. This is a BMW factory. It's fascinating. It's amazing how robot can do things much better than human. Precise and very repeatable, very accurate quality control. But the important point is there's no dynamic physical interaction. This is probably the best contact they have. The little squishy thing is squishing. Look at this. Imagine doing this with you and your friend, like a tilt, push, no, pinching your finger in the corner. This is amazing that the robot can do this kind of thing. So we've been doing this, we've been mastering this for the last 4 or 5 decades. Again, there's no physical contact. Because for manufacturing, that's bad. That's not really good for your manufacturing. You lose your quality control, you lose the repeatability. So in manufacturing world, you want to just purely control position. We're doing really well. But how about a different situation like Fukushima? First of all, robot cannot be anchored to the ground with a 20-inch bolt, very strong bolt. And you don't know what's going on. You don't have all the references. You have to move around. So this person is moving around. Each step is impact. Each step is interaction. Whenever you have a mobile robot, you have to interact with the environment dynamically. Unless you want to move very slowly, right? So people are putting a lot of effort. DARPA invested hundreds of millions of dollars to create this event. No offense for the event, no offense for the engineer. There are a lot of great people working on it. Just look at the robot itself. I just want to point out mechanical design of the machine in terms of impact mitigation. These are still, this is kind of exception actually, I can talk about it if you're interested. They still remain in the manufacturing paradigm. Purely position control, and then when you hit the ground, they cannot handle this impact. It falls in the exactly same configuration because they are all position control. Mostly position control, commanded twice in a minute. Configuration doesn't change when it falls because it's so high impedance and high rigidity. And then they're only commanding position. This is pretty remarkable. I don't know how I'm gonna falling by pushing my finger. There's so high rigidity, high impedance control, so you can actually push yourself off the balance. And some robots even walk on the ground because it's all purely position feeding. This is MIT one. This is actually force control. There's a human factor. This is not the example of the position control, but mostly robots are still using very high gain. I want to make sure I'm in the right position, and then position control. Trajectory optimization, trajectory planning, and so on. So really trying to still minimize the collision and quasi-static. We are still remaining in this kind of old age. If you look at the robots and the competition or all the research robots, there you can roughly categorize into these two categories. One is a manufacturing technology. They're still using high gear ratio, harmonic drive, position control, and Ashimo kind of robot. I'm going to show you Ashimo video as well. lack of compliance. It cannot handle impact. When it comes to impact, there's no control algorithm in a page. You can't have anything. You cannot control anything. You have to really have a right hardware, right impedance shaping and inertia distribution to really handle the impact. And Boston Dynamics and the Mark Rayburn, I think since the 80s, I'm not going to work on electric motors. I have to use a hydraulic because hydraulics are designed to interact with the environment. You need to dig them out. So they are built and very heavy, very strong. The problem is when it comes to mobile application, the efficiency is really, really bad. So they had some improvement. I will show you some data later. And then they need to use a very heavy, very expensive component. I don't think I want to have a hydraulic machine inside my house and then stepping around. And then it's going to be very, very dangerous. And then it's going to be very hot because it's consuming a lot of it. It'd be great in the winter. I'm not sure it's good for summer. So we really need to have a really design paradigm shift from the manufacturing type of machine, maybe with the construction robot as well, but some kind of machine, different type of paradigm. This is just graphics, it's not real robot. DARPA just created. We need to have a different design paradigm to really work on mobile application. So before jumping into this presentation, I want to talk about leg first. This has been debating for many, many decades. And then many people just agree, of course we need a leg. Biology, you have to have a leg to overcome rough terrain. And some people said, that's too complex. It's not going to work. We have a wheel. We invent the wheel. Why do we use the wheel? I think I can tell you at least 2 reasons why we eventually will need a leg system. First is a very popular reason. We need a large workspace to go over rough terrains. I'm not saying leg, just a large workspace. So you can think about the wheeled system that have a large workspace. And second reason is actually a little bit more involved. We need to have a system that can move around in our environment or disaster environment. And then we want the robot not just moving around and capture video. We can do that with quad rotor in our system. We can put surveillance camera everywhere. We want to have some work. We want to at least open the door and then move around. In order to generate some human level force in the reasonable workspace in the high center of mass, you can't have a lower center of mass. You need to have a high center of mass. And you can't have a large footprint. I'm not sure how many people see PR2 from the Wheeler Garage. The wheelbase is like this big. If you have that in your house, it's like an elephant in your house. That can move around in our environment. Imagine myself, I'm 80 kilograms. I only need about a foot by foot footprint to move around almost everywhere. And then I can generate high forces because I have a high center of mass. In order to satisfy these 2 requirements, eventually we're going to have a leg. Some people imagine a wheeled leg system. I actually thought about it very seriously too. I think the complexity is going to kill you. You need to have all the joints required for a leg system and another actuator at the bottom, which is going to be even more expensive. It's going to be much more vulnerable to impacts and getting muddy and getting nasty. So I think eventually, I'm not sure it's going to be human shape or animal shape, but we need to have some sort of articulate system for mobility in an arbitrary environment. Of course, there's a case like the Kiva system. If you are structure your environment, of course we can use another system. But imagine thinking about like a multi-purpose robot, mobile robot. I think eventually we're going to need a leg system. So if you have a leg, you can do something like this. If you provided that you master the controller. This is a snow leopard chasing a mountain goat. I cannot even imagine human will do this. This is only possible quadruped. And there's a many reasons why mammals have 4 legs, but I think we have long enough the evolution time where they can choose to be bipedal or quadrupedal or tetrapedal. They have a tail, we can use it. The majority still remain in quadrupedal. I think there must be a reason. It's unbelievable mobility, and you can see that every step is impact. Of course, copying nature. I'm not going to spend much time. Copying nature is not going to work. There's so much differences. The biggest difference is actually our purpose is different. We're not designing a robot that can send off the safari and then live by itself and surviving, nature. That's not what we want, right? We have our own purpose. And animals are evolved to actually survive in nature, which puts so many different requirements. We're not going to copy and we want to get, bothered by those requirements. We have our own purpose. Somebody will have an elderly care in the house. We put this disaster response at this point. And of course, we actually talked a lot about muscle difference between motors and muscle. That actually give us a lot of challenge learning from animals. And most computer scientists working on this, how can we design artificial intelligence? Of course, manufacturing side, there are a lot of challenges to copy. So we really need to think about what principle we're going to learn. What is really principle of learning? Running. We have to learn how to run. What is running? Not the detail about where the muscles attach and then how the leg lengths, and those are pretty detailed. I think we really understand the dynamics. So I've been working on leg locomotion 14 years, surprisingly. So I've been, this is my favorite project when I was a PhD at Stanford. Using the world's first directional adhesion. It sticks only one direction. I think the Stanford team is still working on it. They recently made a human climber out of the newer version. So one of the students, I work actually at the Harvard, he actually climbed up the wall a few inches, a few feet. This is a project I did when I was my master. This is probably the project that gave me the inspiration. Wow, the running and animal running is actually pretty fascinating. Very simple idea is one motor driving the 6 leg and run about 15 body lengths per second. It's a very simple controller. It's probably not going to work in the high standard master system. This is a very strange robot. This is a squishy, soft robot that has a artificial muscle, SMA, very inefficient muscle that allows to do peristaltic locomotion. It's all fabric, so it's nothing to break. And probably today, most topic is the Cheetah one. I'm going to show you our custom motor, but this is actually all off-the-shelf, the off-the-shelf motor components. It's a little weaker, so it cannot jump high, but actually can run pretty well. And at this point, the robot was constrained in the plane. So it can turn, it can tilt at all. We just test our efficiency mostly. The control algorithm was very simple as well. We use an impedance control, mostly just trajectory feeding with some set impedance. But the efficiency gave us pretty exciting data. The efficiency was almost the same as the animal at the time. So today, mostly talk about the Cheetah project. This robot actually is in the Museum of Science, displayed in the Blue Wing. If you happen to be there, please take a look at it. So, MIT Cheetah, I know it looks like this animal running around, but please take a look at it as a machine that can handle impact, can dynamically control the interaction with the environment. So this is the only electric machine that can run and jump. This is probably the fastest running we can test. We can make it much faster if you have a vision sensor and then make it accurate attack angle. We had a lot of fun last year running in the Killian core, flipping in the Killian core. We can turn, not as dramatic as the animal. Cheetah can turn in a foot or two. We're going to talk about the autonomous jumping a little bit later using the LiDAR sensor. Right, so we're gonna see that later. So I'm gonna skip it. So I'm gonna briefly talk about actuation. It's probably the most critical part of the Cheetah, and then some control idea. We're not developing control theory or algorithm, but more like a paradigm shift also as well, and then some structure at the end for future work. So we talked about muscle-like actuator, like artificial muscle, for a long time. We're trying to develop something like a human muscle. Human muscle is amazing, it's very strong. The challenge is actually just what we need is just too many. We want so many different parameters. We cannot describe as one parameter. Many projects actually, you can boil it down to 1 or 2 parameters. If I achieve really good number in these two parameters, you're good. The problem is the electric motor, the motor for like muscle-like activation. There are too many things you need to satisfy. Not only torque density, you need to have a high torque for the minimum mass. How about high power? There's confusion about power density and torque density. I'm going to briefly talk about it. And back drivability, we talked about not being able to comply when it hits the ground. This is not even quantified. we currently don't have a metric or method to compare one robot, or Hubo, for example, that won the DARPA challenge robot, and hydraulic robot, or even a chimp from CMU. We can't compare how well they're going to mitigate impact. We don't have a metric for that. And contact stability is also very hard. If you have any sensor at the end effector at the hit, and then trying to stabilize the contact, it's become very challenging. You have to mitigate your gains to make sure you have passivity. That really limit your performance. We cannot really do everything with that. And efficiency is also depends on how you run and depends so many different things. Bandwidth is also a big discussion. Like, why do we need a high bandwidth if human is very slow bandwidth? There's a lot of things we can talk about. I think it's not really fair to compare it with the human at this point. But to decide these parameters, we need to really metrics. There's so many other design parameters that are there. We need to decide to make sure satisfy all these. And the relationship between these two are just way too complex. So there's no simple way to represent this is better than this. We have to really create a spider chart. And then sometimes spider chart doesn't really, it's not enough. We have to really show something. So when I started this project, I started looking at all possible actuation technology. And I ended up looking at the electromagnetic actuator. And then this is torque and velocity chart. And then many people told me that you're trying to do something impossible. Showing some biological data. The power density of the electric motors are not nearly as close to the muscle. And so many people say that, well, that's been proven to be impossible. And I looked it up, and then I found completely opposite answer. Muscle power density, it turns out that in vivo testing a human, roughly about 100 watts per kilogram. In vitro test goes higher up, but we don't know if it's sustainable or not. And then I found it's easily a kilowatt per kilogram, or 10 kilowatts per kilogram from electric motor. This is a Tesla motor, and I'm not sure if you've seen the Natick Mall. This is a 4,400-pound machine. It can go 0 to 60 at 4 seconds. If you add another motor, it can go to like 2.9 or something like that. And the one motor case, the motor weight is about 170 pounds out of 4,400-pound machine. And then all the weight is battery. Battery only weighs about 1,000 pounds. It's not about power density of the motor. Motor power density exceeds about 2 order magnitude of muscle. And then last month, 2 months ago, the Porsche guy came in, show off their 22 kilowatt per kilogram motor. There's no match in terms of power density. It's not about power density. So I talked to Jeff Lang, and power density is not a good metric to even talk about. Our muscle is not high power, it's about high force. High force, low impedance. That's actually a very special distinguishing factor of the muscle compared to any other actuation technology. So we focus on, okay, just forget about the power. How can we generate high torque power, high torque, high power, or high torque actuator? So this is a long story and complex story, but eventually we found that if you just increase the radius of the electromagnetic action, so this is what we call the gap radius, the gap between the rotor and stator, the electromagnet, permanent magnet, electromagnet, and then keeping all other dimensions, keeping this thickness, and then increase the gap radius and then reducing the actual thickness, that's always helping. We analyze it. They're theoretically same in torque density and then total inertia. Inertia is really important when you hit the ground, and the reflective inertia is dominating the back ability. And if you ignore friction and the inertia of the gear train, all the transmission, they are same. But when it comes to 200 gear to 1 or 320 gear reduction, all these small frictions and then gear reflected inertia at the end effect is really big. And of course, this assumption doesn't apply when the motor becomes smaller and smaller. So we win a lot by going for right topology, right geometry. So this is a sort of bottom line. Like, what are the kind of actuation scheme we have? This is a typical manufacturing robot. As I showed you in the beginning, very many stages. Well, nowadays all harmonic drive, so it's one stage, but very high gear reduction system. relatively smaller motor compared to the other structure. Very stiff sensor, so to just make sure it stops, but it doesn't prevent from high impact force. And if you look at the performance, like Ashimo, again, I'm not blaming the software. The robot can fail, but watch carefully how it falls. They fall exactly same configuration and roll down the wall. It's become a sculpture. It's a moving sculpture. So you can't really expect this robot to handle unexpected environment and then dynamic movement. This is probably the best performance we've seen out of this paradigm. They add a torque sensor every joint. This is a KUKA arm, and then do impedance control. And then it's pretty impressive. Actually, I play with it by myself, and then I was pretty impressed how much they can reduce the apparent inertia. But watch carefully, this is handled by hand. Such a low inertia, very soft touch. Imagine the bandwidth they're dealing with. It's about hertz or two, 1 hertz or 2. Our Cheetah contact time in the ground is 100 hertz. How can you do dynamic force control capability of 100 or 1 hertz or 2 hertz? How can you do that in handling in 100 hertz and much higher? If you just hit the ground, your force bandwidth goes up easily 100 hertz. So a few hertz of capability, it's not going to happen. So we actually asked the DLR people whenever they came, and then, can you drop it? Can you hammer it? And then they said, no, we can really hammer it back. Another paradigm is this series elastic. It's very popular, and then it's quite successful. I think this is ETH quadruped. They can walk, they can even jump, they can go over rough terrain. Their efficiency is not as good, but I don't think it's because series elastic. I think they can optimize. I think there's a bright future in this paradigm as well. I don't have a good conclusion. I think there's some bandwidth limit, but a series elastic could be very good application, very good method. Rethink Robotics, the Rodney Brooks new company, they actually use series elasticity for making very safe, human-friendly robot. Very cheap price. But we are doing very differently. We are doing, we're really trying to minimize all the inertia and then optimize the geometry and the design of the actuator. So we can actually completely get rid of all the springs and torque sensor to do impedance control. So we can change our spring constant. Now you can be damper. The important part is not just handled by hand. Actually, you can hammer it. That's actually a very important part. Many robots you can just grab the force and torque sensor and then make the impedance lower. But the hammering, the actual impact is actually make it very hard. So you can change this whatever you want anytime in any millisecond. There's no torque sensor, there's no mechanical spring at all. And it is largely inspired by the haptic device. So this is a Ken Salisbury in the 80s. One of his students, I think, designed the startup company. And then they didn't publish the design methodology on this. Like they don't publish about why this is work. There's no torque sensor. This is exactly the simplified impedance control that Professor Neville Hogan actually showed in the 1980s. And then they really go for design. They minimize inertia. They compensate the gravity as much as possible. And then this is easy to measure. And then you can actually control your output force only controlling the torque of the motor. And this is a full dynamics equation from the Professor Hogan's paper. And if you look at this term requires external force measurement. If you don't want to change your inertia matrix, the mass matrix, this term will disappear. You don't need to measure external force. And then we actually don't have any evidence of the inertia shaping. In theory, you can make a 100-kilogram robot, make it feel like a feather in theory, but we actually couldn't make it happen because of the bandwidth or other physical limitations. So if you give up, actually, we don't need to measure. We can just always use a simple impedance control using the torque controller if your inertia is low. So if you design smartly, you can actually do impedance control very well, very simply. Going through impact, that's actually very important, after followed by impact. So this is our Cheetah performance. Blue is the commanded force. So we know the Jacobian results. We can actually command the force at the end effector. And then red is real force measured. They are separate. We just compare them. And then look at the follow, it's not that good, it's like 20% off. But you should have some perspective. This is about 100 milliseconds. This is about 500 Newton, and followed by impact. I don't think we ever seen any data like this. And then we can actually shape this roughly, not very accurate. We can scale up and down very easily. This is a slower speed. If the speed goes up to 6 meters per second, that distance the time becomes 60 milliseconds. Force goes to nearly 1,000 Newton. And we actually are controlling force during that short period of time. This is not control algorithm issue, it's about hardware design. You need to really know how to distribute the inertia to be able to control your dynamic interaction forces in a very short period of time. So for some other robotic application, this could be just an accident, 100 milliseconds. Your blinking eye takes 400 milliseconds. But we have to be able to control. Human running, the ground time is about 500 milliseconds. If you don't have that bandwidth and capability, you cannot control that force. A few advantages of this paradigm, you can actually detect force. It's not really detecting force, actually. We are commanding force based on our geometry. We can actually sense without having force sensor. We actually tried to add a force sensor, and none of them survived more than 5 minutes. Because imagine the impact force in 4 times in a second. We're running like hours of our experiment in our lab. None of the force sensor will survive there. Actually, it's not that different from how humans doing, in my opinion. Our skin force sensors are not very accurate in measuring force. I think it's all Golgi tendon is embedded in our muscle. That's actually dominating our overall dynamics. That's how I believe. I don't think there's any evidence. So this is actually our attempt to quantify the backdrivability. We talk about backdrivability all the time. There's no good metric. We saw that, well, is it backdrivable or not? It's not zero. It's not binary information. There should be some metrics. So our postdoc Patrick actually come up with the idea. Why don't we compare, in order to normalize, compare, we cannot compare 300 kilogram robot to 10 gram robot. So we try to compare worst case scenario impedance when everything is locked. All the joint impedance is infinite, and then we can actually measure the workspace inertia matrix, and then we compare with the existing one, and then we can normalize, and then we can calculate impact mitigation factor. So this is our attempt to quantify backdrivability of the robot. It's mostly dominated by inertia, so there's some caveat. You cannot really quantify the friction. In fact, the friction of here, I'm going to talk a little later, is a nasty problem. It's very complex. And if you have a series elastic and the spring there, all the inertia will be disappearing in this equation, so there's some limitation. So we're trying to come up with an extension of this metric so we can actually cover the stiffness of the system. And this is the friction story. It's very unsatisfactory, actually. One of my students was working on it. This is how the battery energy from battery will, the energy will be distributed in the locomotion. In locomotion, the energy is all dissipated. There's no efficiency because all the locomotion systems, the efficiency is zero because you don't do any mechanical work. So whenever you generate force or torque, you lose the joule heating or some other engine heat loss. And then mechanical system will lose also energy by the transmission efficiency. So this topic is all about the transmission efficiency. The issue is gear friction is different when it's doing positive work and then negative work. So this is actually, we found the first time, everybody speculated, but nobody really tried to capture it. We come with a model that proves it. The problem was the experiment data shows that it's much worse than what actual theoretical prediction. So I'm going to skip all the detail. There's a lot of accurate, repeat experiment and make sure we calculate right. But this is our best data. So this is a dynamic cells it's a kind of servo motor. It's really high quality servo motor, 5 stages per gear. And then look at the positive work, which is all X. And different Newton, different torque. So blue is lower torque, and then red is high torque. And then circle is negative work. They're about 10% difference. And then we didn't know this. The literature didn't know about this. And harmonic drive is getting worse. It depends on velocity. So whenever you do modeling of your robot with any gear, you should really incorporate this. And then look at this. The noise level is really high. It depends on temperature. It depends on lubricant. It depends on preloading and so on. So this is really nasty problem. I think we really need to take a look at more carefully to trust your model. This is also another advantage of our paradigm. We have such a low gear reduction, so low loss in the gear transmission. We can actually regenerate quite a bit. It totally depends on how you're running it, but in this particular drop case study, and we recover about 30% of energy was recovered to the battery. So it's helpful, but it's not actually that much helpful in terms of total energy efficiency. This is the actual running, the measuring all the voltages and current of the battery to measure efficiency. I showed the Cheetah 1 efficiency, which is not that different, but this is like full 3D, so I think this is more like important data. So it ran, it increased speed, and then we stay 4 meters per second for this steady state, and then that's about 600 watt. And then if you don't have a good sense of what it means, it's about your microwave oven is about 1,000 watts, so it's much less than that. Our cost of transport is 0.45. So what do you mean by cost of transport? This is a very popular metric in biomechanics community, where they want to quantify efficiency of locomotion. As I said, you know, when car travel in the flat terrain, you consume all the gasoline power, and then you don't do any mechanical work, so your efficiency is always zero. So they come up with something a little strange. Power divided by weight times the velocity. This is not true metric, because weight and velocities are orthogonal to each other. But that's a convenient tool. So it's a kind of mileage. So if your car mileage like 45 miles per gallon and so on, is a reverse, is a reciprocal of that, and then normalized by the weight, because there's a weight on it. When you talk about car mileage, there's no weight involved, right? So this is a log, minimum cost of transport, the vertical axis, and the x-axis is the mass. So 0 is 1 kilogram, 1 is 10 kilogram, 2 is 100 kilogram, 3 is 1,000 kilograms. So you can see this land animal. There are swimmers and everything. I just did that. This is only land animal. So in this particular metric, heavier animals tend to have a higher efficiency, so lower cost of transport. Human is 0.3, is pretty good, and Honda Ashimo is 2, is about 6 times worse. And Cheetah is 0.4. Hydraulic motion, as I said, is about 30 times worse than Cheetah, even though they're heavier. So if you compare with a similar animal and the similar weight, an animal and a similar weight, it will be about 50 times worse. So their recent version came out, I think is much better. We roughly calculate about 4 or 5, and still older magnitude worse than animal. They're consuming about 10 times more energy to do the same thing. And our Cheetah is 0.45, is exactly the same as the animal. And I'm not proud of that at all, because if you think about electricity and then fat as the quality of energy, is just not matching. So if you use electricity, you should be able to beat animal quite a bit. So we're working on it. If you optimize your design and algorithm, I think we should beat kangaroo. That's our ultimate target. That's like our ultimate hero. So I would like to switch gear and then talk about a little bit of control. The leg locomotion was leg locomotion control was kind of new, but there are a lot of problems in using the conventional control method. So this is just baby step. We don't have any good solution, but it's sort of like an excuse in my opinion. There are the many problems. First of all, the perfect modeling is very hard. There are a lot of methods relying on modeling accuracy. And then contact, especially leg vibration, becomes very, very hard problem. Let alone, as I said, the robot that has a force torque sensor at the foot, and then they cannot even have an impact. So don't even imagine to even matching your simulation. Stability leg locomotion is not defined. You might be surprised, but there's no good metric to define stability. We were working on it. We were trying to define a metric that can tell us how stable you are. This is one of the big challenges. And the real world locomotion is rarely steady state limit cycle. That's typical kind of like a limit cycle is a kind of steady state running, your constant velocity. Imagine if I'm moving from here to my lab or my office, my locomotion will be always in transition. So how can you really quantify or evaluate your algorithm in this transition? It's very, very challenging. So we actually start very simple idea. We try to plan our impulse. So what I mean by impulse is the momentum change. And then that's going to be governing most of the dynamics. And then heuristic feedback will stabilize it. So I'll explain that. So we start, it's actually 2009, I come up with this idea like, okay, so our ground time is so short. I don't think we can control too much on this thing. So we need to come up with some simplified metric that as a target. So my goal was like, I'm gonna find the goal for each step. And then my goal is an impulse, the momentum change. And then I'm gonna just make sure that each step will deliver that. And then that's where the momentum, vertical momentum balance come out. So imagine you're standing or you're jumping up and down, you're running around, walk around. You're constantly losing momentum by gravity, which is just the physics. And then if you're staying in the steady state, you need to compensate that vertical momentum loss by generating gravitational force. I'm standing, so I'm not moving, so my gravitational force is equal to my gravity. But if I'm moving like this, and then if you integrate the vertical force over time, that's the impulse I generated, should be same as mgt, the momentum loss by gravity. So why this is useful, this is a simple physics. If I know how long my leg is in the ground, if I know how long my leg is in the air, and if I simplify, if I approximate this profile, now I can calculate how much impulse I need to generate each step. And then why this is useful? Because I can use for any other speed. The problem of the transition, the third problem is, how many optimizations do you need to run to find the 1 limit cycle? And then, many people work on like, well, 5 meters per second running, this is the solution. But you need to start from 0. You need to accelerate from 0. You need to start from walking maybe. And then how many control I need to design, and then how can you stitch them each other? So we come up with this idea that always globally true, no matter what speed you're running, no matter what rate you're running. And then I know what impulse I need to generate each step. So using this idea, we actually generate many different algorithms. This is a full dynamic simulation and then varying velocity. And then we only changed we don't change any other parameter actually. Our swing time is constant, pretty much constant, and then contact time is governed by the attack angle, leaving angle. Your leg length doesn't change. So we can use one single algorithm to make this run stably from 3 meters per second to 50 meters per second. And of course, we need to add some heuristic stabilization algorithm, which is keeping the body in around the same height using the impedance control. Think about if you control only momentum, means you will guarantee the velocity change if you are successful. But you don't have any guarantee on position. So that's why we need the position-based feedback. But position-based feedback is much smaller. So we had a lot of fun using the same algorithm to like let it jump from the high, and then it ended up being weird gate actually, because there's a central pattern generator and then this feedback, they're fighting against each other, they ended up being weird gate as well. But we actually ended up not using this algorithm because it's just really complex. There's a backbone and there's all the dynamics inertia. So we actually go back to simple, what's one rigid body dynamics, and then we start prescribing the stance time and swing time. So as I said, if I know swing time, stance time, I can figure out what impulse I need. Inversely, if you dominate, if you actually control impulse, we can actually prescribe stance time, swing time. So this is sort of like the ultimate test for us. Can you run or not? So if you can do this, and then which means that I can make it run, because your stance time in the slow speed we can actually dominate, we can prescribe, and maximum once speed goes over 3 meters per second, you have no choice. You have a fixed stance time, so we can actually control. You can actually figure out how much impulse I need to generate, or the other way, I can actually control stance time and swing time. So the simple idea and the simple model, and then the heuristic, just the impedance control and the height and pitch, really allow us to make it stable. And then this is the actual force command in the foot operation space. And then blue is a force profile. As I said, our command profile is very simple. And then only deviation comes from the feedback, the heuristic feedback that stabilizes the system. So ground action force is pretty much dominated by the force control, not the position base. And then that impedance is about 1/10 of what we use for the first Cheetah. Cheetah 1 is mostly trajectory based and then set impedance. So it's a very small spring that's just helping to stabilize in the dynamics. This is our fastest running video. We can try more, but we kind of lost the meaning of why just making line control, running flat train, fastest running. I think we need to go for more versatility. But it was fun testing. And then exactly same algorithm running. We just calculate how much impulse I need to generate in each speed, and then we just increase our desired speed, and then it automatically catching up. And then start getting into weird dynamics. And Professor Park, now he's Professor, you see overlaid magically in the skewed angle of those really fun dynamics. That matched pretty well. So simple dynamics actually is really, really helpful. It's not as accurate as the complex dynamics, but we can calculate quickly and it gives us a lot of insight. Professor Jeff Lang was really helpful on this project. He helped us to develop the MIT motor, which is significantly better than our commercially available motor. Actually, there are better commercial motor, we found that. And we are using only about half of its performance. So it can actually jump twice fast, higher, and run much faster. We are not really, our algorithm is not good enough to use all this power. And we're also, one of the grad students also developing different actuator. But actually, you can actually make a robot run with the commercial motor as well. It's just you can have a more margin there. I want to show you this different project I recently worked on. This is Michael Farid, my student. He designed this exoskeleton suit that allows to jump higher. So as I expected, this is a really challenging problem that we've learned a lot. And the attachment problem of human is just very hard. But this, in this experiment, it was a very dangerous experiment, by the way. We achieved about 13% height increase, including the weight of the system. So he actually jumped higher with about 6 kilogram added mass. And this uncomfortable systems around it. So this is exactly the same motor we used in the Cheetah. I think the exoskeleton need a lot more research. I think we don't quite understand how the testing is with human. But this project was possible only because the motor was very good. This is a collaboration work between Professor Park and then Dr. Wenzing in our lab. And this was last winter to this early this spring. The animals always do amazing thing, and we're trying to use a sensor feedback to really change our gait. And even animal make a mistake when they didn't properly plan it, because planning is very important when you're trying to jump over obstacle and so on. So the two requirements, you need to really adjust the step so that make sure you're in the right position before you're jumping. Second, you need to obviously control the jumping and the landing. And then they work really hard and then achieve this. LiDAR system. So the sensor we have is a 2D LiDAR system that only shoot the laser vertically and then get all this distant data. So this is the ground, and then this is a table, I think, and then this is a ceiling. And then as soon as the obstacle pop up in the environment, adjust the step. So make sure you guarantee the right distance between the obstacle to your robot, and then make sure you're in the right position. And then we run real-time optimization running on a robot like this, and then find the feasible solution in 100 milliseconds. This is only possible because we're using very simple model, and then that's actually good enough to really plan us, allow us to plan. Of course, there's other things we need to take care of, but at least that gives us opportunity to plan in real time. So Patrick is throwing the obstacle, and then he stabilizes it. And then the second one, I think you might be able to see clearly, robot will slow down quickly as soon as you see the obstacle. And then slow down to match the timing. And then various height was working. I'll just jump into the outside jumping. And the outside is actually much easier because you have a much longer distance to cover, to prepare. So you can actually go over 4 or 5 steps to adjust to make sure you're in the right position. So almost you cannot notice any adjustment. And then this is a cheetah view. Headache. This is what we look like if you're actually on a cheetah. So this gives us a challenge for perception people. Like your camera is shaking like this, so you have to get all the right 3D data. And this is show our state-of-the-art filming technology. That is cheetah cart. And then one graduate recruited from other teams. And then we've been working on the turning. I think we're probably going to just jump into the walking and more versatile gait rather than running. I think running is a little bit dangerous, even though it's a good controller in any human environment. So we're trying to bring robots inside the house that can navigate other objects. So briefly explain, it's pretty simple. The gait adjustment is a very simple QP algorithm to minimize the velocity change to make sure you're in the right distance from the goal. And then we pick a velocity that gives us the largest, the smallest the step change. And then this is the actual optimization using very simple model because the one rigid body. The one thing I want to point out here is actually we didn't use any cost function. I think it was really important message for us because we didn't have time to find the optimal solution. What do you mean by optimal solution when you jump over the obstacle? And then if you think about many other tasks we want the robot to do. I want robot to go and then grab a water bottle and then give me a cup of water. If you can do that, so maybe I can ask that to my old mother or old people taking care of the elderly people. What is the cost function on that? What is the optimal? If I open the refrigerator and then grab a water bottle and then clean out, bring the cup and pouring water, what is the optimality here? I don't think we care that much about optimality. We really care about feasibility, the viable. Can you do it or not? Did you drop the cup or not? Did you jam your finger or not? I think we need to think about how to generate automatically non-linear constraint. What do I mean non-linear constraint? I don't want the leg to be hitting my joint limit. I don't want the leg to hit the obstacle. We have this common sense. Human, if you look at many other robotics projects, graduate students write this non-linear constraint in the human coding. And then that's really limit all this workspace, the actual feasible theoretical space. And then your optimization algorithm running inside there. So actual important thing is all done by human. That's why robots are doing only one thing well. If you change the topic, you need to write all these non-linear constraints again. And how can you expect a robot to do many different things? We need to really come up with a way to generate a nonlinear constraint, the common sense automatically, not the finding automatically optimal solution. That's I think we're working on the wrong area. So how can you connect the common sense to the automatically generated constraint? We have to really work on it. I think we're start talking at least in our lab. It's pretty challenging because there are so many different cases. But what we're really lacking in robotics world is actually common sense. How can we automatically encode the common sense? So this jumping example was very insightful for us. Wow, jumping, I don't care if it jumps 30 centimeter high where I spend a little more energy. It jumps, so as long as I don't break my leg by hitting on it. We talked about different actuation scheme, different type of robot, and when it becomes very dynamic, right? If you high torque density actuator, very low inertia minimum, it becomes very dynamic. So it's very hard to deal with. You know, robots. I talked about force control. I talked about not position control. You need to really control the gravity force. Force control is hard because you don't guarantee the position. I mean, we have a position feedback, but the force control dominates. So when some two algorithms conflict each other and doing something weird, it just does fantastically. It's not orientation, it's just purely accidental. This is probably the most scary case. That's why we have a wall in our lab, and then don't ask me why there are holes in the there's reasons for it. Pretty spectacular. Anyway, so you know, this is a hard problem, and I believe that human animals are the same thing. Animals are. I don't think I have a strong stick in computers. I'm very flexible. I'm controlling every time. You can try it. Every time you walk and then put your two hands on the back, every time you walk, you can feel the muscle firing alternatively. So it's not like holding, it's always firing some muscle in the right timing to keep our body flexible, but still very balanced. It's amazing. This is another like a really good inspiration from animal, the human. And we are expert in building momentum and dumping momentum. I call it build and dump. And it's very unstable posture, but like we know how to dump the momentum. This is a more complex, a linear momentum, transition to rotational momentum, angular momentum, and they use that to chain up the body. Pretty amazing if you want to watch it. There's some amazing last moment pronation that adds a little bit of velocity. This is more insight because I'm interested in opening door by robot. And this girl, I don't know, 4-year-old, 5-year-old, is not strong enough to fight against this friction. See how she improvised in a second or two. Push the center as much as possible. That's not enough. Shaking the leg to add more force to fight against friction. It's just amazing. Human is expert on this. So we're trying to really learn this, at least exploit this to in terms of manipulation, power manipulation. So that's the Hermes project where Hermes project is started. So if you can transfer that capability from the robot to human to robot, and we might be able to actually learn how we do, and then we can actually program that in the robot. So the robot might be able to do the same thing. So this video shows that it's hard to see if the Zhuang, the grad student, is wearing something that gives him a feedback, so that he can have some idea of where the stability of this robot. So there are many reasons we're doing this because visual feedback is very slow. There's a lot of processing involved, and then where visual, our vision is used so many different things. So I think perceptive feedback is very important. And then our robot is actually faster than human and stronger than human, so we can actually copy exactly what we do. And I want to just talk about the morphology as well. If you look at the DARPA robotics and robot, they're all kind of human-like, and then they fall and they break the arm, right? If I fall, I might break my arm as well. But one of the reasons is my leg is about 1.6 times longer than my arm. Gorilla, their arm is actually longer than their leg. Arm is about 20% longer than their leg. So falling is quite different, right? The concept of falling in gorilla will be very, very different. They can do quadrupedal locomotion. They can manipulate their arm. I don't know why we need to copy human. It's very bad posture. If your legs are a few feet in the ground, then the falling is just another step. So we don't need to worry about this like stability, crazy stability in the quadruped, in the bipedal. So we actually like this, the morphology. I want to share this video. My grad student, all these 4 people work really hard to really program this idea.
Every year since 1980, an average of 107 firefighters have died in the line of duty in the United States. Thousands of workers die each year in mining accidents. And nearly 250,000 people are still displaced by the Fukushima nuclear meltdown. Gil Pratt, the program manager for the DARPA Robotics Challenge, has stated that if robots were able to take action within the first 24 hours after the cooling system malfunctioned, the first nuclear reactor could have been stabilized.
Here at MIT, our team is trying to fundamentally change how we tackle disaster situations in order to prevent these tragedies. Imagine we could send a robot in a disaster situation instead of risking more lives. Imagine this robot can bring all the capabilities and training of our first responders. This is our vision on how our robotic technology could make our world a better place.
In the last 2 years, we've been working on the Hermes Humanoid system. Hermes is unique because it is designed to be highly dynamic. Powerful motors give it the strength to do heavy work. Light limbs allow fast movements. Flexible hands are robust and designed with the dexterity to use human tools. This is a robot we intend to send into dangerous situations. But Hermes is not alone. A remote operator controls the robot using a motion capture suit, which is custom designed to relay the body's movements in real time. It can allow control of the robot from a distance potentially up to 1 kilometer, while keeping the operator safe from danger. Above all, Hermes protects the life of the human responder. Hermes does what the operator does, harnessing the natural coordination abilities of the human. The operator sees what Hermes sees and feels what Hermes feels. We send the balance sensation of the robot back to the operator using the balance feedback interface. This feedback allows the robot to use the natural human balance reflex capabilities. In a disaster, more than surveying the situation, Hermes can do dynamic physical work. Hermes will learn to walk and run, just like the MIT Cheetah robot. Merging the two technologies will allow the next generation of robots to surpass the capabilities of humans. We are working on the newest generation of disaster situation first responders. We are building Hermes to save lives.
He did that, he put that fire up.
Anyway, so this is a sort of promotion video, but we're trying to really stitch autonomous navigation capability with the teleoperated manipulation. I think when it comes to manipulation, autonomous control is going to be really, really hard. So this is like the message, like I think we're entering a very interesting era where robot will walk with us. This is probably the first in history the leg robot walk with us in the street. Bill Gates was visiting our labs. We had to design something really quickly. So it's not a good controller, but we just make it happen. And then, it's not a very common thing to see in the street in Cambridge. So a lot of people came by and asked a bunch of questions and so on. And I will have a conclusion. I have a couple of future work, but I just want to recap, Perceptive actuation, I think is very important, but we achieve actually all these requirements I put in the slide. It's a very efficient, I don't think it's efficient enough, but it's efficient more than that. And then proptense design, very stable, high bandwidth, contact control. And simple model is sometimes very useful. And optimality, I think, is overrated. We need to really think about what is feasible, what is really the common sense algorithm we need to really impose it automatically, not by human programming. I think robustness is very important. I talk about impact mitigation. Our robots still can break if you fall in a funny way. We need to really design. We need to think about robustness as a really research topic. And real world, as I show you in the gear frictions and so on, is much better than you think. If you want to work on real dynamic robot, you need to really ready to understand the differences in the dirty world. I want to just quickly show a couple of future work. So we're trying to add more perception. We're working with Professor John Leonard. And there are a lot of problems when it's shaking up and down, so you need to tackle this visual stabilization. And when it comes to stereo camera, maybe it's okay. We're not 100% sure yet. When stereo camera case compared to the Tango phone before, it's actually much better. And then nowadays, their stereo camera frequency go up to 100 Hertz, so maybe the shaking is not as bad as the previous case. And also, we're trying to learn more from the animals, really trying to make the robot very strong. We actually learn from this biotensorial structure, make the robot more strong. This is the actual horse leg morphology. It's amazing. All the tendons are wrapped around the bone. This is actually middle finger in your case. And I will show you one video for our sort of showing our goal. This is still my model. Unbelievable. About 250 pounds animal jump up 2-3 story height, all working in tandem and planning. One animal shot the prey, and the second one, okay, you're in the air, you have no choice. And then catch it, and then turn around, slam on the ground, including all the bodies, still survive. It is amazing. And we need to really think about maybe not this level. The robot, make a robot, leg robot, unstable, high center mass. We need to be able to come up with the idea how to make it robust. And this is my last slide. Thank you for your attention, and I'll be happy to take any questions. Thank you very much.
any questions for Simon?
Sorry for overtime, but yeah. Any questions, I'll be happy to answer. Yes?
In the Hermes project, you push on the robot,
Yep.
and the person feels it. How do you generate external force? Is there?
So that's a big question for us too. We're just baby stepping right now. Right now we have this simple potential well that shape our safe region. It's like low force, and then bad region is pushing back. But I don't think that's gonna be our ultimate control, because that only works in the stability control in this sense. I don't think we need that for feedback. When you try to really destabilize yourself, we need a different type of feedback. That's great question for us in the research actually. Yeah. So what kind of feedback? It's not force mapping, right? There's no force that just magically tells the balanced state. So we need to map this balance the state to the operator space. We like to use a force as a feedback, but we don't know what algorithm is the best, most intuitive. Yes.
In the case of jumping over obstacles using the vertical lidar,
Yeah.
every time, so there's a continuous trajectory optimization that's being run, or rather planner.
Oh, the jumping planner is happening only every step. So one of the leg, I think one of the left one leg is hitting the ground and calculate. But ended up using the last one anyway.
Okay.
Yeah.
For the jumping profile, at least it was in the simulation, just show the trajectory that the endpoints of with
That's
the
all that
simplified
matters.
dynamics.
Yeah.
Has there been any work in saving that trajectory profile, that pre-optimized trajectory profile to memory, and then anytime we detect the same situation, we call that kind of jump function, and then maybe modifying it on the fly depending on the changing situation?
Well, so far our obstacle is pretty simple, it's predictable. So, but we should think about it for the next more complex situation. But at this point, we just use a simple algorithm, call it all the time. Yes.
Yeah, the legs tend to move in one plane. What are the challenges, disadvantages, advantages of having them move at skewed angles?
Our leg is actually moving out of plane.
Okay.
It's just not as drastically, so we cannot see it. But we attempt to control the force as well, but the actuator is not something we designed. So that's the next step. We're trying to replace all these extra actuators so we can actually do really 3D force control as well.
I've seen that this robot can run in different velocities, like a transition from. But mostly, I guess, animals have two velocities, like the walking and the running, and there's a fast transition between them. Why do we need to have this all velocities in between for that robot? To just as a luxury, is it like really matter to have the?
Great question. So I think it's the reason why we have to go through all this velocity, because we're not as good as anyone when it comes to acceleration. They're from walking to running in one step. They can do it and they stabilize it. We're not that good, so that's why we need to go through this step. You're perfectly right. Why do we have to have a multiple controller? But how can you make that transition stable? Is an open question. And the traction control should be better. The stabilization should be better. We only know how to just gradually change it. But at least our method allows to a wide range of speed without changing too many parameters.
Notice the feet looks like more like hoops. They don't look like our feet, they look tiny.
Yeah.
What work has been done about having feet that do flex, or is that something you can do?
So we actually spent a lot of time designing right feet and then the right impedance, right articulation. It turns out that if you don't have control over that joint, it becomes just noise and becomes uncertainty. So we just ended up having just a piece of round joint and with some rubbers and some shock absorber. I think in order to have that animal-like ankle, we need to have all the actuator built in. I'm not sure just set passive impedance will give us the right answer. And as you know, your every single toe are all actuated, and you're controlling force every single step. So That's a challenge for robotics. I don't even know if we can afford this so many different little actuators everywhere, especially distal end. We don't want to put anything there. Great question.
Let's thank Sanjay again.